In the previous videos we brought up concepts such as scalars and vectors in mechanics. This video will focus mostly on displacement and distance. So let's remind ourselves of what they are. We define distance to be called the variable s, and then we define displacement to be also s, but with our vector notation, which we call s with a line on top. And this was equal to s x hat plus the y component plus the z component. Like that. In this tutorial, we are only going to consider one-dimensional displacement, and so therefore we are just going to use that the displacement is equal to sx x hat. This means that the main difference is that distance is always going to be positive, i.e. if a box is 10 meters in front of you or behind you, it's 10 meters away. There's no direction given. However, if the box is laid on the x-axis, we could say that sx, this variable here, could be -10 or +10, depending on its position in front or behind of you. Let's have a go at sketching some distance time graphs and displacement time graphs. Let's bring up this example. Here we have a simple set of axes that we can begin to define. We shall mark the distance with units meters, and the time with units seconds, and then the origin. And you can see from our example that the important times are going to be multiples of 5 all the way up to 30. And so we shall draw a series of lines here marking every 5 seconds. Firstly, our car starts from rest and accelerates up until 5 seconds. The car then stays at a constant speed until 10 seconds. When drawing a distance time graph, the speed is denoted by the gradient, meaning that at first we're going to steadily increase the speed, which is going to be a curved line. And so we can draw that like this. Actually, let's go back and do it shallower. After this, the car is going to have a constant speed, all the way up until 10 seconds, like this, marked by a straight line. Then the car decelerates until it stops at 20 seconds. At this point we should probably mark on our times. This will be 5 seconds, this will be 10, this will be 15, and so on. The next instruction is that the car decelerates and stops at t equals 15 seconds, which means to decelerate we'll have a curve, and then from 15 seconds until 20 seconds the car will not move, meaning that the distance will not increase. Then the car reverses, accelerating until 25 seconds, meaning that once again we're going to have an acceleration curve. As we're not doing displacement and distance is the distance the car has travelled, this will be an increase. So therefore we draw a curve sloping up until 25 seconds. Then lastly, the car will brake to a halt at 30 seconds, in which we see a deceleration until 30, at which it stopped again. Let's move on to our displacement time graph. Here we have a second set of axes, which we will label as this time s subscript x with the units meters, and then time with the unit seconds. Then we shall draw our origin on. And we're going to see the differences between the displacement time graph and the distance time graph. Once again, our car starts from rest and accelerates until 5 seconds. So let's draw our seconds marks on again. Firstly, we accelerate up until 5 seconds, which will be denoted by a curve. And then the car stays at constant speed until 10 seconds, which will be a constant line. After this, until 15 seconds, the car decelerates and stops. Therefore, we draw another curved line, meaning it is not travelling any further. It then stays at rest until 20 seconds. At this point, the car reverses, accelerating until 25 seconds. This is where the change begins. Before, our acceleration was denoting the distance the car has travelled, and so therefore it would just increase the amount of distance travelled by the car. However, this time we're considering displacement, so now the car will be travelling back closer to where it was before, meaning the acceleration will be increasing, but the car will be travelling backwards. Therefore, it will look something like this. After 25 seconds, it will then come to a halt until 30 seconds. This means it will decelerate until 30 seconds, and therefore we draw the curve like this. So therefore, you can see when drawing a displacement time graph, it is very obvious that the car has moved backwards towards where it started with this last portion of the example, when this information is not clear with the distance time graph. This means you can get more valuable information from a displacement time graph, which is why it's a lot more useful when studying mechanics. Before we move on, let's quickly denote what different aspects of the graph mean. When observing graphs, we can look at 3 different parts. We can look at the area, we can look at the gradient of the line, and we can look at the rate of change of the gradient of the line. Firstly, the area doesn't mean too much in a distance time graph or a displacement time graph, therefore we won't be considering this. The next thing is the gradient. The gradient of the line, if you were to draw a triangle, would look something like this. In order to find the slope of the line, or the gradient, you would take the change in s and divide it by the change in t to see what kind of step you get. It turns out that when you divide delta s by delta t, you get a speed. Therefore, the gradient at every point is equal to the instantaneous speed at that point. This means if I wanted to know the gradient at t equals 10, I would find out the gradient of this line over here. Lastly, we have the rate of change of the gradient. This will be too hard to calculate in examples, but we can talk about it qualitatively. It turns out that the rate of change of the gradient is somewhat comparable to the increase of the speed, which of course must be the acceleration. The more drastic the slope that you might see here, or here for example, the more drastic the acceleration is. We'll do some examples on this later. If we were to have the same equivalence when considering our displacement time graph, it's very simple. We would have nothing for the area again, but now instead of the speed, we would have the x velocity, and instead of acceleration, we would have the x acceleration. Meaning that when converting from distance to displacement, we can do the same with speed to velocity and acceleration scalar to acceleration vector. Let's move on to an animated example. Next, we move on to the simulated part of the tutorial. This is used so you can get a better idea of how a real-life displacement time graph or distance time graph will be drawn. This animation takes place on the exoplanet TRAPPIST-1d, which these tutorials are based on. Firstly, let's draw the distance time graph. As you can see, over time, the wheel will increase its distance from the starting point at the top of the hill and eventually coming to a stop at roughly 9 seconds. So let's see what we can tell from this graph. At the very beginning, between the points of 1 and 2 seconds, the wheel gradually starts to roll down the hill, meaning there is a slow start, which means that the distance increases slowly with time. And as you can see by this point here, we've only moved roughly 2 meters. You can also tell that the velocity, or the speed, if we're considering scalars, isn't too great at this point either, because the tangent that we can draw to the graph is not very steep, meaning that at this point we don't have too fast a velocity. When we consider times onwards from 2 seconds, it appears that the wheel is rolling down the hill. We can see that the velocity stays roughly the speed it is at exactly 2 seconds, which is faster than before, meaning that it rolls down the hill at approximately the same speed for the next 3 seconds up until roughly 5 seconds. We can see that if we're considering a constant gradient, then the speed is roughly constant, meaning that there is no acceleration at this point. When there has been an acceleration between 0 and 2 seconds, as you can see, there is a slope, and slope is an indication of an acceleration. Beyond 5 seconds, we can see that eventually the wheel comes to a stop at roughly 15 meters from the start point. You can see a deceleration as there is a curve tending towards a lower speed. Let's do the same thing for the Z displacement graph and discuss the differences between the two. As you can see, once again the wheel is rolling down the hill. This time we're considering only the displacement in the Z direction, where Z is upwards. This means that if we're tracking the position of the wheel in only the Z direction, finding the Z displacement, then it's going to be its height at every point, meaning that the graph we have here is actually a representation of the shape of the ground that it's moving on. Now what can we tell from this graph? We can tell once again, as in the distance time graph, that the wheel starts off to a slow start, as there is not very steep acceleration and the gradient is not very steep either, meaning there is a slow Z velocity. However, you can see that after you reach approximately 2 seconds here, the gradient is very steep, meaning we have a very fast Z velocity. This makes sense, as the ball now rolls down the hill. Eventually, when we get to roughly 4 or 5 seconds, it slows down its Z velocity and actually stays at a constant Z displacement for a little bit, before heading back up a smaller hill. Therefore, you can see that from this Z displacement graph, we can get the exact movement of the wheel in the Z direction, showing the shape of the floor below it. This is very valuable information, something that you cannot get from this distance time graph alone. I hope this demonstrates why having both displacement and distance is beneficial. Here we have a distance time graph, so a scalar distance time graph, and we need to find both the distance and the speed at various times. We know from earlier on in the video that the distance can just be read on this graph exactly here. Therefore, if we start off with question 1, we need to find the distance travelled by 3 seconds. We can go to 3 on the x-axis, and we can travel up on the graph, and we get to this point here. And we can see that the value is, in fact, 6 meters. Therefore, if we do the same for question 2, and we go to 8 seconds, and then we go up and we read the value of the line, we can see it's also at 6 meters. Secondly, we need to find the speed. We remember from earlier that the speed, v, is equal to the change in distance over the change in time, which is also equal to the gradient of the line. we're asked to find the speed at 2 seconds. We can see that the graph acts the same between 0 and 3 seconds, as it has the same slope. Therefore, let's write this here. V equals the change in S over the change in t. Now, our graph acts the same between 0 and 3 seconds. As you see, the graph has the same slope until 3 seconds. Therefore, we're going to consider this time period and ignore everything else. We can see that if we write down the change in distance to be the final distance minus the initial distance over the final time minus the initial time, we can say that the final time, or the final distance, sorry, will be 6 meters, as after our time period of 3 seconds, we are at 6 meters, and then we minus off our initial distance, which is 0. Therefore, we're saying that our final is 6 meters and our initial is 0. That shows we're going from 0 to 6 meters. Then we divide this by the final time, which is the end of our time period, 3 seconds, which will be 3, minus our initial time, which we said is 0, as we're considering the 0 to 3 period, minus 0. 6 minus 0 and 3 minus 0 are just 6 and 3 respectively, so therefore we get 6 over 3, which is equal to 2. Therefore we can say that our speed is equal to 2 meters per second. And this makes sense, because if you see, in 3 seconds we moved 6 meters, meaning we moved 2 meters for every second we went forward in time. Let's move on to question 4. Once again, V is going to equal the final distance minus the initial distance over the final time minus the initial time. If you look on our graph, you can see that when considering the flat line, or the time that includes 6 seconds, which is here on the graph, we can consider the time period 3 to 8 seconds, because in that time period the graph acts entirely the same. You can see that the initial distance at 3 seconds is 6 meters, and the final distance at 8 seconds is also 6 meters, meaning that we have 6 minus 6 on the top, meaning whatever we have on the bottom, this is always going to be 0, which shows here that our speed is 0 meters per second, which makes sense, because in the 5 seconds we have not moved anywhere, hence we have 0 speed. Moving on to the second part, we now have a displacement time graph. This means we're now working with a vector quantity. In this question, specifically the y direction, which means now we can have negative values, rather than just the positive values of the distance time graph. Firstly, we need to find the displacement change by 3 seconds. Compared to the beginning, at which we started at 0 displacement, by 3 seconds here, you can see that we have a y displacement of minus 6. Therefore, our change, which I will denote as delta sy in this question, will be equal to minus 6, as this is simply the value at t equals 3 seconds. Of course, I would also allow you to denote this as the change in y, perhaps, or some other form of standard notation for vectors. For 2, once again, the change in y displacement, we go to 8 seconds, as is the question, here, and we read our value off, which is 4 meters. And always remember to put units, as they are stated on the graph. Let's move on to question 3. I shall write down explicitly that the velocity is equal to the rate of change of displacement with respect to time, which means that for the y direction we can write that the y velocity is going to be equal to the change in y displacement over the change in time, which will be equal to the final y displacement minus the initial y displacement over the final time minus the initial time. When considering the period 0 to 3 seconds, we can see the final y displacement at 3 seconds is minus 6. And then we can see that the initial y displacement at t equals 0 is 0, as such, divided by the final time, which is 3 seconds, over the initial time, which is 0 seconds, giving us minus 2 meters per second. Let's go on to question 4. We can write once again the same thing. The final y displacement minus the initial y displacement over the final time minus the initial time. Now we're trying to find the velocity at 6 seconds, which is roughly this point here. We can see that the graph acts the same between 3 and 8 seconds, so we're just going to consider this time period and ignore the 0 to 3 part. We can see that if we consider 8 to be our final time, that the final y displacement is 4, and that the initial y displacement at t equals 3 seconds is minus 6. I'll put that in brackets. Then we divide that by the final time, which we said is 8, minus the initial time, which is 3 seconds. This is going to give us 10 over 5 when you simplify it out, which is now 2 meters per second. This means at t equals 3 seconds, we have the same speed, but we simply switch the direction. Thank you for watching this video tutorial. Visit my website, coherentphysics.com, for many examples with fully worked solutions.